where it's generated, when, where it's gone. I'm going to talk to you for 15 minutes about sedimentology, and the question we're going to address is the question we just had in the room. So after TE8, we had to go back to the basics and really look at the geology and all the data we had on the TAGI to explain why this didn't work. So really the question, why was there very little effective reservoir in TE8? That was a big, big surprise to us. This is just a picture of the TE8 core, actually, and so here's a sand in it, light coloured. You can see a few big pebbles in there, and here's a mud. And in the mud, you can see these white areas, and these are fossil rootlets. And that's part of the story here. The fossil vegetation in TE8 is part of the story. But what I was using this slide to say is that we had to go back to the basics. We had to go back and look at the petrology. Petrology is the description of the rock, the grains. We had to look at the biostratigraphy, the age of this rock. We had to even attempt chemostratigraphy, so to look at the chemical age of the rock. And then we had to go and liaise with a whole raft of experts who we've had out in the field looking at outcrops in Morocco and other places to understand how the TAGI works as a reservoir. So what is the TAGI? So my French is awful. It's the Triassic Argilo-Griso inferior. So it's the Triassic mud sand lower. So it's a clastic deposit. Clastic means it's sand, it's not a limestone. And it's a really mixed deposit. John spoke about how it's quite a poor quality reservoir compared to Algeria. It does work if you stimulate it, but it's not easy. So the TAGI's a real mix of sands and muds and conglomerates. Positively though, we know that it does work. So we've got TE6, and this is an image of the TE6 core. And in TE6, there's some really nice reservoir, which is the red sand on here. And then there are areas which are not so good, which are light coloured here, and they're filled with cement. And the process of filling pores with cement we call diagenesis. I think I mentioned that on the slide. And really, diagenesis is a problem for us because it means you get a nice sandstone full of pores which can hold hydrocarbon, and in geological time they get full of cement and they get blocked up. And really understanding the distribution of pore space in this rock is critical because that constrains how much gas we can get in the rock or oil and how that can flow, so how much we can produce, how much is recoverable. So, one of the studies we did, biostratigraphy. So biostratigraphy, we get some clever guys with microscopes and they go and recover pollen. And these are fossil Triassic pollen, 220 million years old or so from the TAGI, and they can use that they can look at published records of pollen over the world, and they can use that to define the age of the TAGI. And actually now we know that the TAGI is quite late Triassic in age. It's a period that we call a Carnian. It's one of those periods of geological time. And what we know about the Carnian, maybe analogue for the present day, it was a kind of greenhouse system. So atmospheric CO2 was really, really high. It was very hot. It was very wet. Lots of semi-arid places, like North Africa at this time, were subject to kind of monsoonal type conditions. So very hot at certain times of the year, very wet at other times of the year. And those sort of environments, we know, encourage the growth of vegetation. So that's someone's nice fantasy of what the Carnian period looked like in North Africa. So we know the age, we know a bit about the environment. So we mentioned chemostratigraphy. So again, we took all the rock samples from all the wells, and here is an image which shows wells, again, from OSD, it's that same line across the block, through the T5, 6, 8, up to one in the north, JK. And we analysed each of the samples, kind of meter intervals in the tag E, and we tried to chemically correlate them. And this is that chemical correlation. And what's interesting is that T5, T6 is a very nice correlation. We can see these chemical zones. But as you go into T8, it's actually quite different. So it looks like, we know T8 is different in terms of reservoir, but it looks like chemically they're really quite different as well. So we've gone back and we've really looked at the geology of the tag E. And again, I said that the tag E is a real mix of different components. This is the core for T1. So this is the lower part of tag E. And in there, you can see some big quartz pebbles. And they're really angular. So they haven't been rolled about very much. They haven't been moved very far. We call this an immature texture. So this rock, these sediments haven't been moved about much in a river. And we can go and look at tag E in the field as well. We work with a group in Manchester University. And actually, those of you who did the investor trip with John last year, you'd have been to this outcrop. And you've seen this same geology. You can see the pebbles here. It looks just like tag E in our wells. We also see great sandstones in the tag E. So two outcrops here which show actually much cleaner, much more mature rocks. These have been worked around quite a lot. You don't get the pebbles in these rocks. These make brilliant reservoirs. So this is great. And we can also go and look, this is the Manchester guys have been working just to the west of Tenjara, and we can actually see the tag E sitting on the Hercynian unconformity. So we can understand what the topography was like before the tag E was deposited, and that's really important for us, because that allows us to link what we see in the field with what we see on the seismic. Tim's already shown you this slide. But here you can see steeply dipping Paleozoic stratigraphy, and then you can see the Hercynian unconformity with the bright tag E sitting above it. So that's really important. It allows us to understand almost the surface on which the tag E was deposited. So bringing all these things together, we can develop what we call a depositional analogue for the tag E. So we think the tag E, actually in the T5 horst, was deposited in a feature that looks just like this. So this is a modern day image from Death Valley, but what you can see is this wonderful feature which we call an alluvial fan, or a distributive fan. So you've got a river coming out of the mountains here, and then it goes onto a plain, and you get all these small channels coming out here. And this is where you deposit sand and gravel and conglomerates. And this is what the tag E looks like. So that's fabulous. So now we can start to say how big we think the tag E depositional architecture is. And we can say something about the variation of tag E reservoir quality. So again, let's go back to reservoir quality. So what was different between the tag E that works, T6, and the tag E that doesn't work, T8. So these are two thin sections again. So they're a slice of rock, and we shine light through it with a microscope. The scale bar, that's 0.5 millimetre. The scale bar is same on each, 0.5 millimetre. And again, we can see the quartz grains, which are white. We can see some big fragments, look like messy rock. It's like a little pebble, this one. But what's really different, strikingly different about these two rocks is in here you see a lot of blue material. And the blue is space, it's open pore space. And that blue area is where you get gas, where you get oil, and how you can get a rock to flow. And in T8, you don't get any of that blue, you get this nice pinky material. And this is a mineral called calcite in this instance, and it fills all the pores. So there's no space in this rock to put gas, and even if there was, it wouldn't flow because none of those pores are connected. So why is that? Go back and think about our depositional architecture. Where in this architecture do you get good sand, this material, sorry, and where on that alluvial fan do you get this poor material? So this is a published paper, but this is a cartoon of one of those alluvial fans. So the river which comes out of the mountains is here, and you can see this distributive framework coming out from a point source. And what we think we have in Tendrara is that we drilled, or we did, someone else drilled T5, and they drilled it in a nice active river bed. And then we drilled T6 quite close to it, probably in the same area. And then we drilled T7 between them, probably in the same area. And then we drilled T8, and we drilled it probably out of this active channel area. And we drilled it in an area which has probably been vegetated and has developed soils, and those soils have destroyed our reservoir. And we can demonstrate that on this slide. So again, go back to our biostrat. So we know the age of the Taggy, Carnian, it's quite a wet period. And we saw that lovely cartoon of a desert with lots of plants in it. We know deserts actually are pretty wet anyway, and if you've seen some of the weather forecasts in Tendrara currently, it's been raining a lot, and deserts tend to be quite well vegetated. The sandy deserts that you see on TV are pretty rare. And when you get vegetated desert, you produce this material. And these have the wonderrful name of rhizoconcretions, but what they are fossil roots. And they're actually really common. And this material, these fossil roots, they're made of calcite. They're the same material that we saw blocking the pores in T8. So this is our problem. This is what's really destroyed the reservoir quality in T8. Now this stuff can only form where it's not being washed away. So in an active river channel, you don't get vegetation because it can't grow there, it washes away. So this forms in areas where you're not getting reworking of the sediment. So how does that help us build a reservoir model? So this is now a Google Earth image of our same area in Death Valley. I think it's nice because it demonstrates the reservoir models which we're building. So we're looking down now from satellite, but here you can see the mountains on this side, you can see the mountains on this side, and you can see those nice alluvial fans which we were talking about. And we can say you can see a whole series of fans on this side of the valley, and a whole series on this side of the valley. And what's typical about these environments is that in the middle, you get a system called an axial system. So when you get really heavy rain, you get a lot of flow down onto these fans, and everything pumps down the main valley, the axial system. So let's look at that again. So this is just a 3D image of that same area. And let's talk about the wells again. So again, you can see the alluvial fan, you can see the mountains, you can see the axial system. So in that axial system, there is so much energy, there is so much reworking of material that you don't develop vegetation in here. It's too violent an environment for things to grow. And that's an area that we've identified is an area where we can develop good reservoirs. So again, the analogy, 5, 6, 7, drilled in an active channel. 8, drilled in one of these abandoned channels, which is vegetated, destroyed porosity. So what we're looking for then, in terms of A, and in terms of northeast Latvia, is to identify somewhere out in the main channel, the axial channel, where we get reworking, we don't have destroyed reservoir. So that's really what we've been working on. And this is a map. This is not a great map in terms of a visual aid, but this is a map of our block, which really describes our reservoir model. So you'll recognise the block outline. The 5, 6, 7 wells sit here. T8 is this well here. T2 here. SBK here. RR there. The brown, dark brown areas are where we've identified alluvial fans, these nice fan bodies. And the light brown area, sorry, that sort of orangey area, is the area where we think we may get axial systems. This hashed area is where we get no deposition, so these are the mountains. And the light brown area is the fringe of the mountains. So the area, and we've developed this model from the FTG, the data Tim's provided, from the mapping that the guys have provided, and from well data as well. And so we are identifying areas which are shown in the dotted lines here that we think are the axial channels where we get reworking of sediment and we don't get destruction of reservoir. And that's where we've placed the A1 and the northeast Latvia wells. So that's really, stop.
Yeah, I'd like to take a couple of questions.
Sorry, so final slide. So we're a year and a half down the line now. We know a lot more about the Tag E than we did when we drilled TE8. I think we can describe what happened at TE8. We have built a model, but it is still a model. So we've done the best job we can do with this reservoir, with this data. And we think we can identify areas of better reservoir, but reservoir effectiveness, it will remain the key risk in this play. For the reasons I've demonstrated, John spoke about this earlier. So it's a 9 in 10 are located in areas where we predict better reservoir, but it's still the key risk. So I think that's the message.
Take a couple of questions for Jason